Following the initial moments after the Big Bang, the universe was a hot, dense soup of particles. It expanded and cooled rapidly, allowing the formation of the very first atoms, primarily hydrogen and helium, the simplest and most abundant elements. These primordial gases filled space, but were far from evenly spread out. Tiny fluctuations in density, variations left over from the earliest fractions of a second, caused some regions to have slightly more matter than others. These small differences would prove to be crucial in shaping the cosmic structures that followed. At the heart of this story is gravity, the fundamental force that draws matter together. Gravity relentlessly pulls particles toward each other. And in the early universe, this meant that regions with a bit more mass began to attract even more gas and matter. However, ordinary matter, the stuff atoms are made of, did not act alone. A mysterious, invisible substance called dark matter played a pivotal role here. Though it doesn't emit or absorb light and remains undetectable directly, dark matter constitutes about 85% of the total matter in the universe. Its presence is inferred through its gravitational influence on visible matter, light, and the large-scale structure of the cosmos. Dark matter acted as a scaffold on which the first galaxies could assemble. Because it interacts primarily through gravity, it clumped faster than ordinary matter, which was hindered by pressure and radiation in those early times. As dark matter pulled together, it formed dense clumps known as dark matter halos. These halos provided gravitational wells deep enough to attract and hold onto the gas made of hydrogen and helium. Without dark matter, the gas alone wouldn't have been able to form galaxies as quickly or as effectively, since the gas pressure would resist collapse. The process of gas falling into these dark matter halos is the first key step in galaxy formation. As the hydrogen and helium gas was drawn into the gravitational wells, it began to compress and heat up. If the gas could cool efficiently, it would collapse further, eventually forming dense clouds capable of igniting nuclear reactions at their cores, birthplaces of the first stars. But gas cooling in the young universe was no simple task. Without heavier elements, or metals, in astronomical terms produced later by stars, cooling pathways were limited. Primordial gas mainly relied on molecular hydrogen, H2O, to lose heat through radiation, but forming molecular hydrogen in the early universe was a slow and delicate process. Despite these cooling challenges, regions within the dark matter halos eventually succeeded in forming stars. The first stars were likely much more massive than those commonly seen today, many tens or even hundreds of times the mass of our sun. Their immense size and brightness drastically altered their surroundings. These so-called population III stars lived short, explosive lives, producing heavy elements through nuclear fusion that were then dispersed by stellar winds and supernova explosions. This enrichment of the interstellar gas with heavier elements enhanced cooling processes for subsequent generations of star formation and contributed to the evolution of galaxy formation. As the population of stars grew within these dark matter halos, their collective gravity began to pull in even more gas, allowing galaxies to gradually assemble and grow in size and complexity. Smaller halos and their fledgling galaxies often collided and merged, building larger and more massive structures over time. These merging events not only increased the mass of galaxies, but also triggered bursts of star formation by compressing gas clouds, a dynamic process still observed in the universe today. Moreover, the process of reionization had a critical impact on the formation and evolution of galaxies. The ultraviolet light from the first stars and galaxies ionized the surrounding neutral hydrogen gas, turning it into a highly energetic plasma. This epoch of reionization changed the conditions for gas cooling and galaxy growth throughout the universe. Understanding how reionization proceeded remains a major focus of current observational and theoretical research. Modern telescopes, both in space and on the ground, are now probing the distant universe to directly observe galaxies as they were forming billions of years ago. By studying the faint light from these ancient systems, scientists are piecing together the timeline of galaxy formation and testing the predictions from cosmological models. The patterns observed in the cosmic microwave background radiation, the residual glow from the Big Bang, also provide a snapshot of the initial density fluctuations that seeded this entire process. In essence, the formation of the first galaxies was a complex interplay of cooling gas, gravitational collapse enhanced by dark matter, and the feedback effects from the very first stars. This intricate sequence of events set the stage for the diverse array of galaxies that populate the universe today. From the elegant spirals like our Milky Way to the massive elliptical galaxies and irregular forms seen across the cosmos. To summarize, the journey from a nearly uniform gas after the Big Bang to the rich tapestry of galaxies began with microscopic density variations amplified by the gravitational pull of dark matter. This invisible halo structure provided the blueprint where ordinary gas collected, cooled, and birthed stars, which then drove further galaxy growth through energy output and chemical enrichment. Each piece, gas, dark matter, and gravity, was indispensable to this cosmic construction project, revealing how the complex universe emerged out of a simple beginning. Building on this foundation, it's important to explore how the early structure of the universe itself influenced the timing and scale of the first galaxy's formation. The universe's expansion played a double role. It stretched space and diluted matter over vast distances, yet it also created the conditions necessary for gravity to gradually take hold in localized regions. This interplay between expansion and collapse was delicate. If the universe expanded too quickly, matter would spread out too much, preventing significant clumping. But since the rate of expansion decreased over time, pockets with more mass eventually overcame this stretching, allowing gravity to win locally and initiate the process of structure formation. One of the key insights from cosmologists came from observing the cosmic microwave background, CMB, the afterglow of the Big Bang. This faint light, pervasive in all directions, reveals tiny temperature fluctuations corresponding to density variations in the early universe. These fluctuations acted as the initial seeds around which matter gathered. Astronomers can map these variations with high precision, thanks to satellites like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck mission. Such observations confirm that the universe began with slight irregularities, perfectly consistent with the theory of cosmic inflation. A rapid expansion phase in the universe's first moments that magnified quantum fluctuations into macroscopic density differences. These seeds grew over hundreds of millions of years as dark matter's gravitational pull gathered gas into dense regions. Once a dark matter halo reached a critical size, on the order of hundreds of thousands to about 1 million times the mass of the Sun, the forces within became strong enough to trigger gas collapse and star formation. These mini-halos are thought to host the birth of the universe's first stars. Yet, not all mini-halos were destined to become galaxies. Some were too small or had their gas heated and dispersed by radiation from nearby stars or by shock waves from supernovae. Understanding the balance between collapse and disruption helps scientists determine the timing and efficiency of galaxy formation. Indeed, the feedback effects from the earliest stars had profound consequences. When these massive population III stars exploded, they injected enormous amounts of energy into their environment. This energy heated surrounding gas and drove powerful winds that could expel gas from shallow gravitational wells, temporarily halting further star formation within their host galaxies. This feedback created a form of cosmic regulation, where the growth of the very first galaxies was not simply a continuous process, but rather one marked by bursts of assembly and periods of relative quiet. At the same time, these energetic processes began to influence neighboring regions, facilitating a gradual transformation of the intergalactic medium. The radiation and shock waves from early stars and supernovae spread heavier elements, or metals, into the space between galaxies. This enrichment altered the chemical makeup of subsequent star-forming clouds. The presence of metals allowed gas to cool more efficiently. Metals have many energy transitions that emit radiation, which carries heat away and enables gas to condense to higher densities more quickly. Through this enrichment, the universe transitioned from a primordial state dominated by hydrogen and helium to one where more complex chemistry could take place. This transition extended to the formation of the first normal or population II stars, which were less massive and longer-lived than their predecessors. Consequently, these stars contributed to the gradual buildup of more stable, prolonged star formation within nascent galaxies. The process also influenced the morphology and dynamics of early galaxies, encouraging more structured formations like disks and clusters. Over time, as galaxies accumulated more stars and gas, they began exhibiting traits recognizable in modern galaxies: rotating disks, collective stellar populations, and dynamic interactions with their surroundings. Beyond the formation of individual stars and galaxies, cosmologists are keen to understand how these early structures organized themselves on larger scales. The large-scale cosmic web, a network of filaments and voids, became an important aspect of the universe's architecture. Galaxies often reside at the intersections of these filaments, where dark matter, gas, and galaxies flow and merge. The first galaxies were no exception. Their locations and interactions were influenced by this cosmic scaffolding. Through processes of accretion along filaments and mergers within dense nodes, galaxies increased their mass and complexity. Mergers deserve particular attention, as they not only contributed to galaxy growth, but also shaped galaxy morphology. When two young galaxies collided, enormous amounts of gas could be compressed suddenly, sparking intense bursts of star formation, sometimes called starbursts. These events could transform the structure of a galaxy, turning disks into more spheroidal shapes or triggering central black hole activity. Today, observations of both nearby galaxies and those in the distant universe confirm that mergers play a central role in galaxy evolution, dating back to these early cosmic times. Another fascinating aspect of early galaxy formation involves the growth of supermassive black holes. Evidence now suggests that even the first galaxies hosted massive black holes at their centers. These black holes, millions to billions of times the mass of our Sun, significantly affected their host galaxies through powerful jets and radiation, a process known as active galactic nucleus, AGN, feedback. How these black holes grew so rapidly in the early universe is an area of active research, but their feedback effects likely helped regulate star formation by heating or expelling gas from the galactic centers. At the same time, astronomers examine how the universe's large-scale environment altered the efficiency of galaxy formation. Dense regions, destined to evolve into galaxy clusters, developed more rapidly than underdense areas, which remained relatively sparse and quiet. This environmental variation helps explain why we see a diversity of galaxies today, from crowded clusters rich in ellipticals to isolated spiral galaxies like our Milky Way. Tracing back these environmental influences allows scientists to connect the dots between the earliest structures and the cosmic landscape we observe now. One of the major current frontiers in this field is the study of high redshift galaxies, galaxies so distant that their light has taken nearly the entire age of the universe to reach us. These galaxies are glimpses into the youth of the cosmos, seen as they were just a few 100 million years after the Big Bang. Technological advancements, such as the deployment of the James Webb Space Telescope, JWST, have revolutionized our ability to observe these early objects. JWST's powerful infrared instruments allow scientists to detect the faint glow of stars and gas in galaxies that formed during or just after the epoch of reionization. Through these observations, researchers not only measure the properties of early galaxies, their sizes, masses, star formation rates, and chemical compositions, but also test theoretical models of galaxy formation. Early results reveal galaxies that challenge some expectations, showing surprisingly rapid star formation or chemical enrichment. These findings require refinements in our understanding of the speed and complexity of early galaxy growth. Simulations play a crucial complementary role alongside observations. Using powerful supercomputers, scientists create detailed models of cosmic evolution based on the laws of physics and initial conditions inferred from the CMB. These simulations track how dark matter, gas, radiation, stars, and black holes interact over time. They have confirmed many core aspects of the galaxy formation picture while uncovering new questions, such as the role of turbulence in gas clouds, the impact of radiation pressure from stars, and the complex interplay between gravity and magnetic fields. Another area gaining attention is the role of gas flows in and out of galaxies, a process known as galactic baryon cycling. Galaxies grow by accreting fresh gas from their surroundings, but they also lose gas through winds driven by supernovae and AGN feedback. This continuous exchange regulates star formation and chemical enrichment. In young galaxies, these gas flows may be especially turbulent and powerful, shaping their development and eventual fate. Looking forward, plans for new telescopes and observatories promise to deepen our grasp on the universe's early chapters. Radio observatories like the Square Kilometer Array, SKA, aim to map the hydrogen gas during the epoch of reionization, providing a direct view of how the first luminous objects transformed the intergalactic medium. Likewise, next-generation space telescopes will enable deeper, sharper imaging of primordial galaxies, revealing their structure and star formation in unprecedented detail. Ultimately, the story of the first galaxies is a narrative of transformation. From simplicity to complexity, from uniformity to the rich diversity we see today. It is a story written in the language of physics and told through faint light traveling across billions of years. By decoding it, we learn not only about distant galaxies, but also about our own cosmic origins, tracing how the elements that compose stars, planets, and life itself were forged in those earliest galactic nurseries. As research continues, each new discovery adds another piece to the puzzle of galaxy formation, sharpening our picture of how the cosmos evolved from a nearly featureless primordial fog to the magnificent cosmic tapestry we inhabit. This ongoing journey of exploration and understanding underscores the profound human quest to know where we come from and how the universe around us came to be. A crucial factor enabling the first galaxies to assemble was the role of cooling processes within the gas clouds drawn into dark matter halos. Initially, the gas in these regions consisted largely of hydrogen and helium, left over from the Big Bang. For gas to collapse and form stars, it must lose energy and cool enough to become dense. Without effective cooling, gas remains hot and diffuse, resisting gravitational collapse. In the primordial universe, cooling was a challenging task because the gas was nearly free of heavier elements, or metals in astronomical terms. Metals here include any element heavier than helium, such as carbon, oxygen, or iron, which are produced later in stars. These elements are vital for efficient cooling because their atoms and molecules have many ways of emitting radiation, allowing gas to shed heat quickly. In the absence of metals, the gas primarily cooled through the emission of radiation from hydrogen molecules, H2, and, to a lesser extent, helium. The formation of molecular hydrogen was a slow and delicate process, primarily facilitated by trace amounts of free electrons acting as catalysts amid the neutral hydrogen gas. Despite these hurdles, this limited cooling enabled the gas clouds in mini-halos to reach temperatures around a few hundred kelvins, sufficient for the formation of the first massive stars. As the first stars ignited, their radiation triggered changes in local chemistry and heating, which sometimes inhibited further star formation nearby, but also paved the way for more complex structures elsewhere. When these early stars went supernova, they expelled metals into the surrounding space, enriching the interstellar and intergalactic medium. This metal enrichment became pivotal for the next generations of galaxies, as the presence of metals dramatically improved cooling efficiency, allowing gas to fragment into smaller clumps and form stars of lower masses and longer lifespans. These generations included population II stars, more similar in characteristics to those observed throughout much of the universe today. This gradual enrichment also influenced the shape and composition of early stellar populations. Rather than single, isolated stars, later phases saw star clusters and stellar associations form more readily, contributing to the cohesion and gravity within embryonic galaxies. As these clusters accumulated, they fostered more complex gravitational potentials, attracting more gas and dark matter, and assisting the growth and stabilization of protogalactic systems. Simultaneously, the sites where dark matter halos and gas congregated were not random, but followed patterns imprinted in the earliest fluctuations of the cosmic microwave background. The cosmic web of filaments, walls, and voids determined where matter preferentially gathered, influencing the spatial distribution of the first galaxies. This large-scale structure funneled gas towards the dense nodes where multiple filaments converged, facilitating the growth of increasingly massive halos capable of sustaining vigorous star formation and complex galactic dynamics. Within these dense cosmic environments, interactions between nascent galaxies became increasingly common. The gravitational pull between nearby proto-galaxies led to mergers and accretion events, which not only increased their mass, but also infused energy into the systems. Such interactions could stir gas, compressing it further and igniting bursts of star formation. These starburst episodes rapidly converted gas into stars, altering the brightness and appearance of early galaxies and affecting their evolution. Over time, the balance between gas inflow from cosmological filaments, star formation, feedback from stars and black holes, and gas outflow established a dynamic equilibrium critical to sustained galaxy growth. The importance of feedback mechanisms cannot be overstated in this process. The energy output from massive stars, in the form of ultraviolet radiation, stellar winds, and eventual supernova explosions, had the power to heat and expel gas, preventing runaway star formation that might consume the galaxy's entire fuel supply prematurely. This regulatory role is analogous to a thermostat controlling a heating system, maintaining conditions favorable for steady development rather than chaotic collapse or rapid exhaustion of resources. Black holes, which likely formed early within these dense galactic centers from the remnants of massive stars or direct collapse of gas clouds, also contributed to feedback mechanisms. When black holes actively accreted matter, they released tremendous energy, creating active galactic nuclei, AGN, that could heat surrounding gas or drive powerful outflows. This interplay influenced the ability of galaxies to form stars and evolve structural features such as disks and bulges. Consequently, black hole growth and galaxy formation are intimately linked, each shaping the other as galaxies assembled. Over the first billion years, the cumulative effects of these processes transformed small, irregular collections of stars and gas into more organized and sizable galaxies. Astronomers classify many observed early galaxies as dwarf galaxies, meaning they are smaller and less massive than systems like the Milky Way. Despite their size, these dwarf galaxies played an outsized role in cosmic history, especially in the reionization of the universe. Reionization refers to the epoch when the ultraviolet light from young stars ionized the neutral hydrogen gas in intergalactic space, making it transparent to light and ending the cosmic dark ages. The first galaxies, through their star formation and radiation, were agents of this fundamental transformation in the universe's state. The structure and development of these earliest galaxies also set the stage for hierarchical galaxy formation, a concept in which small galaxies merge to form larger ones, gradually building up the variety of galaxy types observed at later times. Over billions of years, successive mergers and accretion events led to the formation of large spiral galaxies, elliptical galaxies, and other diverse forms that populate the contemporary cosmos. By studying the fingerprints of these processes in the light from distant galaxies, astronomers reconstruct the timeline and mechanisms involved in the growth of cosmic structures. The continual inflow of fresh gas from cosmic filaments remained essential for sustaining star formation in growing galaxies. Without a steady supply of new gas, galaxies would deplete their star-forming material and become dormant. This inflow often occurred in the form of cold gas streams that could penetrate hot gaseous halos surrounding mature galaxies, replenishing the supply even as other gas was heated or expelled. The understanding of these gas accretion channels helped resolve long-standing questions about how star formation persisted over cosmic time. At the same time, observations revealed that not all galaxies grew smoothly. Some experienced periods of quiescence, where star formation slowed drastically, often linked to environmental factors like gas stripping in dense clusters or feedback processes strong enough to shut down gas inflow. These quenched galaxies play important roles in the life cycle of the cosmos, representing states in which galaxies balance their gas content and star formation activity in ways not always predictable. Modern telescopes and instruments continue to peel back the layers of this history. Surveys harnessing gravitational lensing, where massive foreground objects magnify the light of distant galaxies, have allowed astronomers to study faint and tiny galaxies from the earliest epochs. These observations confirm theoretical predictions about the sizes, star formation rates, and morphologies of primitive galaxies, while also uncovering unexpected features that challenge existing models. In particular, the discovery of galaxies at ever-increasing distances pushes the boundary of cosmic time closer to the Big Bang itself. Detecting galaxies from less than 400 million years after the Big Bang offers glimpses of the very onset of galaxy formation, inviting questions about the efficiency of star birth and the interplay of dark matter, gas, and radiation under such primitive conditions. These findings stimulate ongoing refinements in understanding the balance between physical processes driving collapse and those providing feedback and regulation. The formation of the very first galaxies thus emerges as a story shaped by gravity's slow but persistent accumulation of matter into specific regions of space, enabled and complicated by the physics of gas cooling, star formation, energetic feedback, and cosmic environment. Each galaxy's journey to maturity weaves together these elements in unique ways, producing the astonishing variety we observe across the universe. As new research deploys ever more sensitive instruments and sophisticated simulations, the picture of early galaxy formation gains clarity without losing complexity. Scientists gain awareness of additional factors influencing the process, such as magnetic fields, cosmic rays, and the influence of dark energy on large-scale structure growth. These elements enrich the field and invite continued exploration of one of the most profound questions in modern astronomy: how the first galaxies came to be, and with them, the foundation of the universe's luminous architecture. Building upon the understanding of how the earliest galaxies formed and evolved through processes of gas cooling, star formation, feedback, and mergers, one crucial aspect arises: the role of cosmic reionization in shaping the environment for these primeval structures. Reionization marks a dramatic phase in the history of the universe, when the pervasive neutral hydrogen gas that filled space after the cosmic dark ages was ionized, stripped of its electrons, by high-energy ultraviolet light from the first luminous sources, including stars and galaxies. This transformation had profound implications for galaxy growth and cosmic evolution, setting the stage for the universe as we observe it today. During the epoch of reionization, which began roughly 400 million years after the Big Bang and lasted a few hundred million years, the radiation emitted from the first generations of massive stars accumulated, creating bubbles of ionized hydrogen in the intergalactic medium. Initially localized around individual galaxies or groups of galaxies, these ionized regions gradually expanded and merged, eventually filling the cosmos. Observations now suggest that reionization was patchy and inhomogeneous, with some areas ionizing earlier than others depending on the density, star formation rate, and clustering of galaxies in those regions. The process of reionization had a dual impact on galaxy formation and evolution. On one hand, the energetic photons that ionized the hydrogen gas also heated it, increasing its temperature to thousands of kelvins. This heating raised the pressure of the intergalactic medium, making it more difficult for gas to collapse gravitationally into smaller dark matter halos, especially those with masses less than about 100 million solar masses. In other words, the increased temperature created an obstacle known as the genes filtering mass, beyond which gas could no longer efficiently fall into potential wells to form stars. Consequently, reionization could suppress or delay star formation in low-mass halos, selectively influencing the population and properties of the smallest galaxies. On the other hand, reionization is partly the outcome of galaxy formation itself. A feedback loop emerges where galaxies produce the photons that reionize space, while the evolving ionized environment in turn modulates which galaxies can continue to grow. Understanding which galaxies contributed most to reionization remains a key, ongoing research question. Current evidence points to small, faint dwarf galaxies as the primary contributors. Although individually modest in brightness, these galaxies were numerous and prolific star formers in the early universe, collectively supplying a sufficient number of ionizing photons to drive reionization. However, confirming this requires observations pushing the limits of modern telescopes, since these faint galaxies are challenging to detect directly. To glean insight into reionization and early galaxy formation, astronomers leverage multiple techniques. One principal method involves studying the absorption lines in the spectra of distant quasars, extremely bright active galactic nuclei powered by supermassive black holes. As light from these quasars travels through intergalactic space, it passes through hydrogen gas clouds, leaving distinctive absorption imprints called the Lyman alpha forest. Before reionization completed, the gas was largely neutral and opaque to ultraviolet light, causing strong absorption signatures. Observations show that at redshifts corresponding to about 1 billion years after the Big Bang, the Lyman alpha forest transitions dramatically, indicating the late stages of reionization. These measurements provide a timeline against which galaxy formation models are tested and refined. Meanwhile, space telescopes like the Hubble Space Telescope have contributed significantly by detecting galaxies at redshifts approaching 11 or higher, meaning their light has traveled over 13 billion years to reach us, revealing the universe as it was mere hundreds of millions of years after the Big Bang. The properties of these early galaxies, such as their star formation rates, sizes, and ultraviolet light output, offer clues about their capacity to ionize their surroundings. Upcoming observatories, including the James Webb Space Telescope, JWST, built specifically to observe the infrared wavelengths that penetrate cosmic distance and dust, are already revolutionizing this field by identifying even fainter and more distant galaxies, potentially pushing observations to epochs closer to the formation of the first stars themselves. Beyond the cosmic scale, the internal structure and dynamics of these nascent galaxies provide insight into their formation processes. Studies reveal that the earliest galaxies were relatively small, often a few thousand light-years across, much smaller than a mature galaxy like our Milky Way, which spans over 100,000 light-years. These proto-galaxies often exhibited irregular shapes, lacking the well-defined spiral or elliptical forms common in the local universe. This irregularity reflects the turbulent, rapidly changing conditions within early galaxies, where bursts of star formation, supernova explosions, and gas inflows combine to create complex and dynamic environments. The buildup of angular momentum, or rotational motion, in these young galaxies is another area of interest. How and when galaxies developed organized spinning disks has implications for understanding galaxy morphology and the formation of stellar populations. Simulations indicate that as gas was funneled through cosmic filaments into dark matter halos, it often acquired angular momentum through tidal torques, the gravitational interactions between neighboring structures. This rotational momentum encouraged the gas to settle into rotating disks, setting the stage for the formation of galaxy structures that would evolve into the familiar spirals seen in the modern universe. Chemical evolution within the first galaxies also adds an important dimension to their story. As the earliest stars lived out their short, fiery lives, they synthesized heavier elements in their cores and dispersed them through supernova explosions into the surrounding gas. This enrichment allowed subsequent generations of stars to form from gas clouds with increasing metallicity, which influenced the physical properties of stars and the cooling efficiency of gas clouds. Observations of distant galaxies increasingly capture the signatures of this chemical buildup, enabling astronomers to trace the timeline of cosmic metal enrichment. Furthermore, the formation and role of massive black holes in early galaxies intertwine with these developmental themes. While the exact origins of supermassive black holes remain an area of active investigation, evidence suggests that some black hole seeds originated from the collapse of massive primordial gas clouds or the remnants of particularly massive early stars. These black holes could grow rapidly by accreting gas at high rates, generating intense radiation and powerful jets observable even at great distances. The feedback from active black holes not only regulated star formation, but also contributed to shaping the environments of early galaxies. On the observational front, astronomers use detailed computer models and large cosmological simulations to explore galaxy formation under a variety of physical conditions. These simulations begin with the initial conditions set by the Big Bang and track the gravitational growth of dark matter structures alongside the hydrodynamics of gas. By including physical processes like star formation, feedback, cooling, and chemical enrichment, researchers can generate virtual universes to compare with actual observations. This synergy between theory and observation refines our understanding, revealing, for instance, how different feedback scenarios affect the size and luminosity of early galaxies, or how merger histories influence the diversity of galactic forms emerging over cosmic time. Scanning a bit closer to home, astronomers can also study so-called near-field cosmology, which involves examining the local universe to glean clues about the earliest cosmic epochs. Dwarf galaxies in the local group, the cluster of galaxies including the Milky Way and Andromeda, often have stars with very low metallicity, interpreted as relics from early cosmic times. These nearby ancient stars can provide a fossil record, containing in their chemistry and distribution the imprint of early star formation and galaxy assembly, supplementing distant observations that look back in time. The first galaxies set the foundation not just for stars and black holes, but also for the larger cosmic structures that came to dominate the universe. Their assembly marked the initial phase of a cosmic hierarchy, whereby galaxies grow and cluster, bound by gravity into groups, clusters, and superclusters. This vast interconnected structure shapes the large-scale distribution of matter, influencing galaxy interactions, star formation histories, and the evolution of cosmic morphology over billions of years. In conclusion, the formation of the first galaxies is an intricate narrative woven from cosmic inflation's initial fluctuations, the enigmatic yet dominant influence of dark matter, the physics governing ordinary matter's cooling and condensation, the feedback from the earliest luminous sources, and the grand-scale influence of reionization. These early galaxies, though small and chaotic by today's standards, played a pivotal role in laying the universe's luminous framework, setting countless paths for the diversity and complexity that followed. Modern astronomy's expanding capabilities continue to illuminate this formative epoch, bringing us ever closer to understanding the earliest chapters of cosmic history. As we delve deeper into the story of how the first galaxies formed, it becomes essential to consider the influence of dark matter, not just as a passive backdrop, but as a dynamic architect of structure in the early universe. Although dark matter remains invisible and mysterious in nature, its gravitational effects are undeniable. It formed the scaffolding on which ordinary matter, or baryonic matter, could gather, cool, and ultimately ignite the stars that made galaxies shine. Dark matter is thought to have clumped into vast halos early after the Big Bang due to tiny fluctuations in the initial density of the universe. These halos were not uniform spheres, but rather complex filamentary structures woven into a cosmic web, guiding the flow of gas. Ordinary matter, attracted by the gravity of these halos, fell in and began heating up due to collisions and compression, forming hot gas clouds. This hot gas then needed to cool and condense, processes governed by the physics and chemistry of the primordial elements such as hydrogen and helium, to collapse further and reach the densities required to spark star formation. In the absence of heavy elements, which play a key role in cooling gas through radiative processes, cooling mechanisms were limited primarily to molecular hydrogen. Despite being fragile, molecular hydrogen acted as a critical coolant in these first clouds of gas. It allowed the gas to lose energy, reducing pressure and facilitating collapse into compact regions dense enough to birth the first stars. This phase marks what astronomers call the population III stars, the very first generation, formed directly from primordial gas. These population III stars were likely very massive, much larger than typical stars seen today. Without metals to regulate their formation, they could reach hundreds of times the mass of our Sun. Their lifetimes were short but spectacular, ending in supernova explosions that not only expelled heavy elements into the surrounding medium, but also generated shock waves. These shock waves compressed nearby gas, triggering subsequent rounds of star formation and contributing to the chemical enrichment necessary for more diverse stellar populations. The seeding of these early galaxies by population III stars thus initiated a chain reaction. The heavy elements produced and dispersed by their deaths changed the cooling dynamics of gas clouds, allowing denser and cooler clouds to collapse more efficiently and form stars of various masses, including those similar to our Sun. This transition also altered the opacity, structure, and thermal properties of the forming galaxies, shaping their evolution in new ways. Yet beyond individual stars, the assembly of larger galactic structures depended heavily on the merging of smaller dark matter halos. Over time, these mini-halos combined through gravity to form progressively larger halos, in a process known as hierarchical structure formation. This bottom-up growth meant that the first galaxies were built from the amalgamation of smaller protogalaxies and star clusters, gradually increasing their mass and complexity. As these mergers happened, gas within the interacting halos was compressed, sparking waves of star formation, sometimes called starbursts, that could outshine the galaxy's usual brightness by orders of magnitude. However, mergers were far from peaceful events. They stirred up turbulence, redistributed angular momentum, and often triggered feedback processes such as intense radiation or powerful outflows propelled by stellar winds and supernovae. These factors worked in concert to regulate how efficiently a galaxy could convert gas into stars and shape the galaxy's morphology. Intriguingly, the balance of gas accretion and feedback influenced the ultimate fate of early galaxies, affecting whether they evolved into quiescent, slowly star-forming systems or remained lively, star-bursting environments. Understanding this interplay remains a central challenge in piecing together the evolutionary path from small, chaotic high-redshift galaxies to the diverse forms observed in the present-day universe. Another critical factor affecting the growth of the first galaxies were the cosmic inflows of cold gas along the filamentary structures of the cosmic web. While merger-driven bursts contributed sporadically to galaxy mass, more steady gas streams along filaments provided continuous fuel for star formation. These cold gas flows, avoiding shock heating that would raise the gas temperature and inhibit collapse, fed galaxies efficiently and maintained their star-forming potential over extended periods. This mechanism highlighted the connection between the large-scale cosmic environment and the fate of individual galaxies. Denser regions of the universe, such as the nodes of the cosmic web where multiple filaments intersected, became fertile grounds for early galaxy clusters. There, intensive merging and gas inflow led to rapid growth, making these regions precursors of the massive galaxy clusters we observe today. On a related note, the formation of early galaxies played a significant role in the eventual emergence of large-scale cosmic structures. As dark matter halos merged and galaxies formed within them, gravity pulled these structures closer together, forming groups and clusters. This clustering influenced the rate of galaxy-galaxy interactions, such as mergers and tidal encounters, which in turn affected gas dynamics, star formation, and black hole activity. Speaking of black holes, the earliest galaxies are also closely linked to the birth and growth of the universe's first black holes. Observations have revealed luminous quasars, powered by supermassive black holes, for periods corresponding to when the universe was less than 1 billion years old. The presence of such massive black holes during this early epoch raises questions about how they formed so quickly. One pathway involves the remnants of the first massive stars collapsing into black hole seeds, which then accreted gas rapidly to grow into supermassive black holes. Alternatively, some theories propose direct collapse of exceptionally massive gas clouds into black holes millions of times the sun's mass, bypassing star formation. In both scenarios, the black hole's accretion and associated energetic output could regulate their host galaxy's evolution through feedback effects, heating and expelling gas, quenching or triggering new star formation cycles. Current and next-generation observational facilities are poised to shed light on these questions. The James Webb Space Telescope, in particular, is revolutionizing studies by peering further back in time and resolving the conditions around these nascent black holes and their host galaxies. Understanding early black hole growth provides a crucial piece of the puzzle in the broader narrative of galaxy formation and cosmic evolution. As we consider these formative processes, it's important not to overlook the role of magnetic fields and cosmic rays, less well understood but potentially significant factors in early galaxy evolution. Magnetic fields can influence gas dynamics, star formation, and the behavior of charged particles, shaping how galaxies evolve internally. Similarly, cosmic rays, high-energy particles accelerated by supernovae and black hole jets, can impact the interstellar medium's temperature and chemistry, potentially altering star formation. While direct observations of magnetism and cosmic rays in the earliest galaxies remain beyond current capabilities, simulations and theoretical work suggest they could provide important feedback mechanisms, influencing gas flows and the structure of the interstellar medium. Efforts to characterize these effects continue to advance alongside improvements in computational astrophysics. Turning now to observational evidence, distant galaxies provide snapshots of galaxy formation across cosmic time. By studying galaxies at a range of redshifts, astronomers assemble a timeline of how galaxies grew, changed, and matured. Patterns emerge showing how average galaxy size, mass, star formation rate, and metallicity evolved, revealing phases of rapid growth and slow, quiescent aging. One of the striking discoveries is how quickly some early galaxies reached large masses, billions of times more massive than the Sun, despite the young age of the universe at those epochs. This rapid buildup suggests highly efficient gas accretion and star formation in select environments, possibly boosted by merging activity or focused inflows along dense filament intersections. Conversely, many galaxies remained small and faint, consistent with a scenario where the majority of early star formation occurred in these dwarf systems, as discussed earlier in the context of reionization. This uneven growth highlights the importance of environment and initial conditions in determining each galaxy's evolutionary trajectory. These observations also assist in constraining theoretical models. For instance, the luminosity function, describing the distribution of galaxy brightness at given epochs, provides a key testbed. Comparisons between predicted and observed luminosity functions inform adjustments in assumptions about star formation efficiency, feedback intensity, and the properties of interstellar gas. Furthermore, gravitational lensing, whereby massive foreground objects bend and magnify light from distant galaxies, has become an invaluable tool for studying otherwise inaccessible faint, distant galaxies. These natural, cosmic telescopes allow astronomers to probe smaller, less luminous galaxies thought to dominate the early universe's population, providing critical insights into the full diversity and behavior of primordial galaxies. In recent years, multi-wavelength astronomy has also played an increasingly prominent role. Early galaxies emit radiation across the electromagnetic spectrum, from radio waves produced by cold molecular gas to high-energy X-rays emitted by black holes and supernovae. Observatories sensitive to different wavelengths piece together a holistic view of galaxy formation, revealing the interplay between stars, gas, dust, and black holes. For example, radio telescopes detect the presence of cold molecular gas, the raw material for star formation, allowing scientists to estimate the fuel available in early galaxies. Infrared observations, particularly with telescopes like JWST, penetrate dust and trace star-forming regions obscured in visible light. X-ray observatories identify energetic processes linked to black holes and supernova remnants, providing clues about feedback mechanisms and galaxy growth regulation. Altogether, integrating data across the electromagnetic spectrum enriches our understanding and helps to reconcile theoretical predictions with real cosmic structures. Another dimension to consider is the role of dark matter annihilation or decay and its influence on early galaxy formation. Although this remains speculative, some theoretical work explores whether energy released from dark matter particles could have subtly affected gas cooling, star formation, or the timing of reionization. While current evidence does not confirm these effects, future observations and experiments may shed light on possible indirect influences of dark matter physics on baryonic structures. Returning to the evolutionary thread, the progressive buildup of complex galactic features, from simple star clusters to organized spiral arms and bulges, unfolded over billions of years, but its roots lie in the early formative stages. Disk formation, triggered by the accumulation of gas with angular momentum, eventually led to large rotating stellar systems. Bulges and central stellar concentrations could emerge from mergers and dynamical instabilities, while extended halos formed from stars scattered during these violent events. The interplay between internal and external processes is evident here. Internal feedback from stars and black holes shapes the galaxy from within, while environmental factors, neighbor galaxies, dark matter halos, and cosmic filaments exert influence from the outside. This delicate balance continues to be a central theme in understanding galaxy formation and evolution, not just for the first galaxies, but throughout cosmic history. In summary, exploring how the first galaxies formed leads naturally to appreciating their multifaceted nature. Gravity-driven assembly guided by dark matter, star formation regulated by cooling and feedback, complex chemical evolution, and the coevolution of black holes. Continual gas accretion, interactions, and environmental factors make galaxy formation a dynamic, emergent process rather than a simple, linear path. As observational capabilities and theoretical tools improve, our picture of this epoch becomes increasingly detailed. Scientists unravel the physics behind each process and begin to reconstruct the narrative of cosmic dawn with precision. From the tiniest dwarf galaxies acting as reionization agents to the emergence of massive, active systems hosting supermassive black holes, the first galaxies stand as milestones in the universe's journey from simplicity to complexity. This ongoing exploration underlines one of the most exciting frontiers in modern astrophysics. Understanding not just where galaxies come from, but how the fundamental forces and ingredients of the cosmos conspire to create the structures that eventually led to planets, life, and observers capable of asking these very questions. To deepen our understanding of how the first galaxies came into being, it is essential to consider the role of star formation efficiency within these primordial cosmic structures. Star formation efficiency refers to the fraction of gas within a galaxy that is converted into stars over a given period. In today's galaxies, this efficiency varies widely, influenced by factors such as the galaxy's size, composition, and environment. However, in the earliest galaxies, these efficiencies were governed by very different conditions compared to the present day. In the immediate aftermath of the first star formation episodes, the gas reservoirs within emerging galaxies were relatively pristine, containing primarily hydrogen and helium. Without heavy elements, or metals, as astronomers call all elements heavier than helium, gas cooling was less efficient, making it more difficult to condense large amounts of gas into stars quickly. Yet, the strong gravitational potential wells of the growing dark matter halos helped hold onto the gas and maintain sufficient densities to sustain ongoing star formation. The interplay between gravity, gas cooling, and feedback from nascent stars determined star formation efficiency. Feedback mechanisms, the processes by which stars return energy and materials to their surroundings, played an especially crucial role. For example, radiation pressure from young, massive stars could heat surrounding gas and push it outward, regulating how much gas remained available for subsequent star formation. Similarly, supernova explosions from the first massive stars not only dispersed heavy elements essential for enriching the interstellar medium, but also drove powerful shocks that could both trigger and suppress star formation in nearby gas clouds. The net effect of feedback often acted as a self-regulating mechanism to prevent unbounded star formation, which would otherwise rapidly consume the available gas. This regulation was vital in shaping early galaxy evolution, slowing their growth in some cases, while in others, intense bursts pushed galaxies to produce stars at rates significantly above average for their size. Another factor influencing star formation efficiency was the initial distribution of angular momentum within the collapsing gas clouds. As the gas cooled and contracted, any small rotation present, imprinted by large-scale motions in the cosmic web, was amplified, causing the gas to spin faster. This spin prevented direct radial collapse, leading instead to the formation of rotationally supported disks. The presence of disks within these first galaxies meant that star formation was in some ways organized, with gas settling into thin, rotating structures where gravitational instabilities could lead to localized star formation. These disks, if massive enough, could become gravitationally unstable themselves, forming clumps of gas dense enough to trigger rapid star formation. Over time, interactions and mergers between protogalaxies could also induce bars or spiral patterns within disks, further influencing the star formation activity by funneling gas inward or stirring it up. A significant insight about early star formation efficiency comes from the comparison of different galaxy masses. Smaller galaxies, often termed dwarf galaxies, generally have shallower gravitational wells, making it easier for feedback processes to expel gas. Consequently, their star formation efficiency tends to be lower because intense feedback events can blow out a significant fraction of the gas, reducing the material available for future star formation. Conversely, more massive early galaxies, embedded within bigger dark matter halos, were better able to retain their gas despite feedback. This allowed more sustained or even rapidly increasing star formation, helping them grow quickly and form the large stellar populations observed in some early massive galaxies. This dichotomy influenced the luminosity and mass distribution of the first galaxies, creating a diversity of systems ranging from tiny, faint dwarfs to rapidly star-forming massive galaxies. The presence of dust also began to emerge as an important factor over time, altering star formation efficiency. Initially absent in the pristine gas of the first stars, dust grains began to form through the cooling ejecta of supernova explosions. Dust contributed to cooling processes by facilitating molecular hydrogen formation and provided surfaces on which gas molecules could stick and cool more rapidly. Moreover, dust could absorb ultraviolet radiation from stars, protecting molecular gas from dissociation and further promoting star formation in dense regions. By enhancing gas cooling and shielding, dust gradually increased star formation efficiency in later generations of early galaxies, accelerating their transition toward more complex and efficient star-forming systems akin to familiar galaxies seen in the closer universe. Turning to the global picture, astronomers use various observational proxies to estimate star formation efficiency at early cosmic times. For instance, measuring the luminosity of galaxies in ultraviolet light, primarily emitted by young, massive stars, helps estimate the star formation rate. Combining these rates with estimates of gas mass, obtained via radio or submillimeter observations of molecular gas, allows researchers to infer the efficiency with which galaxies convert gas into stars. In the early universe, star formation rates showed a remarkable range, with some galaxies producing stars at rates hundreds of times greater than our Milky Way today, albeit over much shorter timescales. This frantic pace often indicates episodes of starburst activity, typically triggered by mergers or gas accretion events, illustrating the dynamic nature of early galaxy assembly. Despite these vigorous star formation episodes, the earliest galaxies often remained small, due in part to the limited availability of gas and the disruptive impact of feedback. In some cases, the combination of strong radiation fields and energetic outflows from stars and black holes could suppress star formation temporarily, producing phases of quiescence followed by rejuvenation. Understanding these cycles is crucial because they set the stage for the long-term evolution of galactic populations. Galaxies that could effectively regulate their star formation, avoid catastrophic gas loss, and maintain or replenish their gas reservoirs were more likely to grow into the diverse galaxy types observed locally, from elliptical galaxies and spiral systems to lenticular and irregular morphologies. An additional nuance in early star formation involves the initial mass function, IMF, of stars, the distribution of star masses at birth. As mentioned previously, the very first stars, population III, were predominantly massive, but with increasing metal enrichment, the IMF is thought to have shifted toward a distribution more similar to that observed today, with many lower mass stars. This shift in the IMF affects the feedback and chemical enrichment patterns of early galaxies. Massive stars inject more energy and metals into their environment, but live shorter lives. while lower mass stars contribute mass loss over longer periods and can survive to be observed as fossil records of early star formation epochs. As observational technologies improve, astronomers increasingly seek to constrain the IMF in early galaxies by examining their integrated light, chemical abundances, and supernova rates. These efforts not only advance understanding of star formation efficiency, but also provide insights into stellar evolution and the chemical evolution of galaxies. Another frontier concerns the interplay between star formation and the growth of supermassive black holes within early galaxies. Many early galaxies host active galactic nuclei, AGN, powered by accreting black holes. The energy output from AGN, often outshining the combined stellar light of the galaxy, can have profound effects on the galactic environment. AGN feedback can heat the surrounding gas, drive powerful outflows, and prevent gas from cooling and collapsing to form stars. This mechanism becomes particularly important in the most massive galaxies and galaxy clusters, where it is believed to regulate or even quench star formation on large scales. However, the relationship between AGN activity and star formation is complex. In some cases, AGN-driven shocks or outflows can compress gas in certain regions, triggering new star formation episodes rather than suppressing them. The timing, intensity, and spatial distribution of AGN feedback relative to star formation determine the overall impact on galaxy evolution. Observational evidence for AGN star formation interaction in early galaxies comes from the detection of simultaneous bright starbursts and powerful AGN emissions in the same systems, alongside detailed spectroscopy revealing the dynamics and composition of the interstellar medium. Studying this delicate balance via multi-wavelength observations, from X-rays that highlight AGN activity to infrared emissions tracing dusty star-forming regions, helps build a clearer picture of how galaxies co-evolve with their central black holes. Aside from these internal factors, the environment of early galaxies played a pivotal role in shaping their evolution. Galaxies were rarely isolated in the young universe. Instead, they were embedded within networks of filaments and nodes comprising the cosmic web. These environments strongly influenced gas inflows, merger rates, and the assembly of galaxy groups and clusters. Denser environments facilitated more frequent and sometimes more violent interactions among galaxies. Such interactions fostered the exchange of gas, stars, and dark matter, fueling star formation and black hole growth in bursts, but also could strip gas and stars from galaxies, leading to quenching of star formation in some cases. The environmental dependence of early galaxy formation is evident in the observed clustering of galaxies at high redshift, with some regions showcasing overdensities of galaxies, precursors of the galaxy clusters that dot the local universe. These protoclusters provide laboratories to study the interplay between galaxy formation and large-scale structure. Connecting this to cosmic reionization, the process that made the universe transparent to ultraviolet light after the cosmic dark ages, early galaxies are considered the primary drivers of this fundamental transition. The ultraviolet photons produced by massive stars in early galaxies escaped into the intergalactic medium, ionizing neutral hydrogen and fundamentally changing the state of the universe. The efficiency with which galaxies produced ionizing photons and allowed them to escape is tightly linked to their star formation activity, feedback processes, and internal structure. Understanding these factors is thus inseparable from tracing how the first galaxies formed and evolved. Recent observations using facilities like the James Webb Space Telescope, JWST, and large ground-based observatories are pushing the frontier of observing galaxies within the epoch of reionization, providing new constraints on their properties, star formation efficiencies, and roles in cosmic reionization. Finally, insights from sophisticated computer simulations have become invaluable in bridging theories with observations. These simulations model galaxy formation and evolution by incorporating physics ranging from gravity and hydrodynamics to radiative processes, star formation, and feedback. While challenges remain, such as accurately modeling the detailed physics of feedback or cosmic magnetism, simulations have successfully reproduced many observed properties of early galaxies, including their mass distributions, star formation rates, and chemical enrichment patterns. They also predict how early galaxies evolve across time, merge to form larger structures, and build complexity. By combining observations, theory, and simulations, the quest to uncover how the first galaxies formed continues to advance, revealing an intricate, dynamic cosmic history in which the seeds of the modern universe were sown. Beyond these fundamental processes shaping the first galaxies, one of the most profound aspects is how these early structures paved the way for the vast cosmic landscape we observe today. The initial conditions set by the first galaxies influenced not only their own evolutionary paths, but also the growth of larger-scale structures in the universe, including galaxy groups, clusters, and the intricate networks formed by dark matter and gas across billions of light years. Early galaxies acted as the cosmic building blocks, merging and interacting over time to form increasingly massive and complex systems. This hierarchical model of structure formation, supported by both observations and simulations, explains how small proto-galaxies combine to create the grand spirals, ellipticals, and irregular galaxies visible in the local universe. Mergers spark bursts of star formation and can radically alter galaxy shapes, funnel gas towards central regions igniting active galactic nuclei, or redistribute angular momentum, all contributing to the galaxy's evolution. One key demonstration of this growth is seen in the difference between the first galaxies and their descendants several billion years later. The earliest galaxies were often small, low in mass, and relatively simple in structure, whereas by the time the universe was a few billion years old, many galaxies had amassed far more stars and developed organized features such as spiral arms or central bulges. This progression highlights the importance of both internal processes, like star formation and feedback, and external influences, such as mergers and environmental factors, in shaping galactic evolution. Chemical enrichment also represents a fundamental legacy of the first galaxies. The heavy elements produced within stars and spread by supernovae gradually changed the composition of the gas reservoirs from which new generations of stars formed. Over time, this chemical evolution enabled the formation of planets, molecules, and dust grains, effectively triggering the transition from the pristine, metal-poor gas of the earliest epochs to the chemically rich environments of later cosmic times. Without the dispersal of these elements by the first galaxies, the universe would lack many features essential to the formation of planets and life as we know it. Connecting this chemical story to observable evidence, astronomers study the composition of very old stars within the Milky Way and other nearby galaxies. Some of these stars carry the chemical fingerprints of early enrichment events, offering clues about the nature of the first supernovae and the stellar populations in primordial galaxies. These stellar relics act as cosmic archaeologists, allowing researchers to piece together the conditions that prevailed when the first galaxies were taking shape. Another intriguing direction in the study of early galaxies is the role of cosmic magnetic fields. While not fully understood, magnetic fields could influence the dynamics and structure formation within galaxies. They may affect how gas cools, collapses, and forms stars, and impact the behavior of charged particles and cosmic rays. Observations and simulations suggest that weak magnetic fields might have been generated in the early universe, amplified by processes such as turbulence and star formation feedback within first galaxies, thus contributing additional complexity to galaxy formation and evolution. Expanding on the topic of galaxy environments, it is important to consider the influence of the cosmic web. the vast network of filaments consisting primarily of dark matter and gas that cradled early galaxies. Galaxies often formed at the intersection of these filaments, where material flowed in along the web, fueling growth and enabling the accumulation of gas needed for star formation. These filaments also guided the interactions and mergers among galaxies, shaping their evolution in ways that depended heavily on their location within the cosmic web. Denser regions, known as nodes, where many filaments converged, tended to host more massive and rapidly evolving galaxies, often the progenitors of rich galaxy clusters observed today. In contrast, galaxies forming in more isolated or less dense regions had slower growth rates and might have remained relatively small for extended periods. By studying the distribution of galaxies and their properties across different environments, astronomers gain insights into the environmental dependency of galaxy formation, shedding light on why galaxies exhibit such diversity in morphology, size, and activity. A significant development in recent years has been the use of deep galaxy surveys at multiple wavelengths, ranging from X-rays and ultraviolet to infrared and radio waves, to identify and characterize early galaxies in unprecedented detail. The James Webb Space Telescope, for example, has opened a new window into the epoch of galaxy formation by detecting faint galaxies that existed less than 1 billion years after the Big Bang. These observations reveal not only how star formation and chemical enrichment progressed, but also how early galaxies contributed to reionizing the universe. The data collected from these surveys allow scientists to construct galaxy luminosity functions, graphs that show how many galaxies are found at various brightness levels in the early universe. This helps quantify the number density of galaxies at different epochs and track the growth of stellar populations over cosmic time. The luminosity functions indicate that, while bright, massive galaxies existed early on, the majority of galaxies were faint and small, aligning with the idea that hierarchical merging is a dominant growth mechanism. In parallel, advances in spectroscopy enable measurements of the gas kinematics, composition, and temperature within these distant galaxies. Spectroscopic studies often detect emission lines from ionized gas, which help determine star formation rates, gas metallicities, and the presence of active galactic nuclei by comparing spectroscopic properties across different redshifts. A measure of cosmic time, astronomers reconstruct the narrative of galaxy assembly and evolution. One fascinating insight from spectral studies is that many early galaxies exhibit signs of significant outflows, fast-moving winds driven by stellar feedback, or AGN, which suggests that energy and material were escaping back into the surrounding intergalactic medium. These outflows are critical because they regulate star formation within galaxies and contribute to the enrichment and heating of the intergalactic gas, thereby influencing subsequent galaxy formation in nearby regions. Moreover, as researchers probe the earliest epochs, the transition from the formation of population III stars to the predominance of population II stars becomes clearer. This shift marks a fundamental change in the types of stars forming within galaxies. While population III stars were massive and short-lived, their explosions seeded the environment with metals, allowing population II stars to form with a wider range of masses and longer lifetimes. This transition impacts the ionizing photon production crucial for reionization and affects the feedback processes governing galaxy growth. Another layer of complexity arises when considering the presence of gas inflows. While outflows remove gas, galaxies also continually accrete fresh material from their surroundings. These inflows, often funneled through the cosmic web filaments, provide the fuel needed to sustain star formation. The balance between inflows and outflows largely determines a galaxy's star formation history, and ultimately its size and shape. Simulations have demonstrated that gas inflows can be smooth or clumpy and can occur along cold streams, a mode where gas remains relatively cool, avoiding shock heating as it falls into the galaxy's gravitational well. Such cold accretion is thought to dominate in low-mass halos and early times, providing a steady stream of cool gas that promotes efficient star formation even in galaxies with relatively shallow gravitational potentials. In contrast, in more massive halos, gas falling in typically experiences shock heating, which can inhibit immediate star formation by maintaining gas at temperatures too high for rapid collapse. Here, feedback processes from stars and active black holes can interplay with inflow characteristics, causing variations in star formation rates and galaxy morphology. Investigating these inflows and outflows observationally is challenging, but becoming increasingly feasible with instruments capable of high-resolution spectroscopy and imaging. Tracing the motion of gas within and around galaxies helps clarify how galaxies regulate their growth. Some studies observe extended gas reservoirs or streams around high redshift galaxies, lending support to cold gas accretion scenarios predicted by simulations. The assembly of the first galaxies also sets essential groundwork for the eventual formation of galaxy clusters, the most massive gravitationally bound structures in the universe. As galaxies merge and gather into larger systems, they contribute to the intracluster medium, an extremely hot and dense gas permeating galaxy clusters. The properties of this medium, including metallicity and temperature, reflect the cumulative influence of countless star formation and feedback episodes over cosmic history, beginning with the very first galaxies. Understanding the buildup of these large structures offers insight into cosmology itself, as their abundance and distribution are sensitive indicators of the universe's composition and evolution. Consequently, research into early galaxy formation connects deeply with fundamental questions about dark matter, dark energy, and the underlying physics governing cosmic expansion. Looking ahead, the next steps in studying the formation of the first galaxies involve pushing the limits of observation and simulation. Upcoming ground and space-based telescopes, such as the Extremely Large Telescope, ELT, the Square Kilometer Array, SKA, and proposed future missions, will provide even more detailed data across a broad range of wavelengths. These facilities will help answer outstanding questions about the initial mass function variations, the role of magnetic fields, the details of gas dynamics, and the connections between galaxy growth and large-scale structure. Simultaneously, continuous improvements in computational power and modeling techniques are enabling simulations to include the tiniest relevant physical processes, from molecular cooling chemistry to radiation hydrodynamics and cosmic magnetism, all crucial for accurately capturing the emergence of the first galaxies. By integrating these developments, astronomers are beginning to form a comprehensive picture of how the earliest galaxies transformed cold, dark, and uniform cosmic matter into the incredibly rich and diverse tapestry of galaxies populating the current universe. These insights not only satiate human curiosity about our cosmic origins, but also frame the conditions necessary for the genesis of stars, planets, and ultimately life itself, connecting the cosmic past with our own existence.